Okay, today we're going to be talking about networks. The plan for the day is to go through the PowerPoint here, just in the chapter. The PowerPoint is already in the learning plan, so you can take a look at that. That's fine. Sort of follow along or just use it as a self-study guide. We'll also be doing 3 review questions. We won't be doing any of the lab exercises or the lab manual this week, just because it does involve a lot of group work and having people together. We may follow up in another class. Most of you have taken Networking 1 or in Networking 1 or will be taking Networking 1 starting next semester, and you'll see a lot of review in there. This chapter is really just an overview of that entire course. Some of the technical skills also, like when we talk about cabling, you'll be making cables or have made cables in that class as well, so we're not going to spend a ton of time in those areas. This is a very broad overview. In this chapter, we're talking about the basic functions of the network, including the common devices and connectors, the difference between LANs and WANs, and how TCP/IP sort of affects all that. Performing basic resource sharing, how do we share printers and data and so forth. Pretty typical network is just like this picture. We have a local computer, that's the computer that you're on, and remote computers are other computers. The picture sort of makes it show or look like it's different rooms. It could be, or it could all be the same room. It could be just with the classroom right now. We're all talking together, and we all have stuff that we can share depending on how our systems are set up. The exact same idea happens when we work with the internet. The only difference is that we're not sharing with something next to us or across the room. We're sharing with something that's most likely remote location, like a web server. We say, hey, can I get this information? And the reply is, sure, I want to share that with you. Sometimes we even go a little bit deeper in that what we connect to, then it connects to something else. Storage is a big, big example of that. Sheer volumes of data and videos or music or whatever are stored in its own network. Web servers that can access that. We access the web servers access the storage devices, and it's sort of a tiered approach, but it is all just a big network. So what do we do in a network? We share things. That's another reason we have them. When personal computers first came out, they were truly that. They were personal computers, that you did your work, the other person did their work, you stored your files, they stored their files, and everybody in the office needed a printer. It sort of seemed kind of not very efficient for everybody to just have those silos and have all the redundant equipment. So that's where networks came out. And here's a specific example of sharing a printer, but you could just as easily share files as well. Now you only have to have one printer per office or 1, 2, 3 printers per floor or whatever. So you're not having everybody having to have their own devices, but it's all because of sharing. So instead of passing floppy disks around, you are being able to just access them directly across the network. So let's talk about some of those network topologies. A typical network looks like this. You're going to have a server and some clients. That's a client-server topology. They can share within each other, but most of the communication is happening with the server to the computers directly. And there's whole other sections talking about peer-to-peer and client-server. But this is just a very typical. What connects all these devices together? It's the little box in the middle called a switch. And the switch allows that traffic to be managed and to go where it needs to go. So when one device sends a frame, it knows where to route that frame. Topology is the physical and logical design of the network to connect all the devices together. The most common type of topologies are bus, ring, star, and mesh. Later on, I'm going to talk about keeping the two ideas separate. Physical is how it looks on a piece of paper. Logical is really how the bits and the frames all flow across that network. It sort of talks you through some of these on these next couple slides. Here it talks about, but we have pictures coming up that make it much more clear. Again, making a clear distinction between the logical and physical. Logical is how it's laid out on paper. Physical is how it's I'm sorry, logical is how the network is laid out on paper, of showing how the traffic flows. Physical is what it looks like if you actually drew how the wires are going. Okay, looking at some of the topologies, we have a bus. It's a nice straight line. One computer is connected to the next. This was the physical way of first connecting computers together when the first networks came about. You literally ran a cable from one computer to the next, and to the next, and the next. It's one long straight line. So that's a physical bus in that you were physically connected one to the other, and it's also a logical bus. The traffic did pass that way from one computer to the next, the next, the next, and finally got to go where it needs to go. In your networking 1 class, you learn a little bit more about details of that. The issue with bus networks is if there's a break anywhere in the network, it fails it ceases to function on the entire network, not just between those two devices. So it's a little bit harder to troubleshoot. Very easy to expand. All you do is plug another computer at the end and then continue on to the next one. The bus and the ring are nearly identical in their advantages and disadvantages. The ring is just taking that bus and wrapping it around from end to end. Just sort of taking it around there, and that makes your ring. Again, extremely easy to add. All you do is unplug the cable from the one computer, plug it into the new one, and then drag your cable over to the new computer. Same issues though with troubleshooting. If there's a break anywhere on the network and you wouldn't know where, it would in fact bring the entire network down. Gallup Morris, an advantage of this is that it doesn't require any special equipment. It's just the wire connecting to each computer. The computers do need the network interface cards to allow the wire to be there, but no central connectivity device. Newer typologies are the star network. The star is having some kind of connectivity device in the middle, and that can be various devices. This chapter is really going to concentrate on just one, just the simple switch. And the switch allows that traffic to go from one computer to the other to the other. Later on, we're going to talk about actually Ethernet, of how we have a physical star, but having a logical bus in there. And again, when we get to that picture, it'll make more sense. A mesh is sort of the most complete type of network. Every device is connected to every other device. The advantage of this are quite clear, that if I'm communicating with the device across the network, I have a direct connection to it. I'm not competing for it with anybody else. I don't have to worry about congestion because I'm the only person talking on it, and very, very nice and clean that way. It's also great for redundancy. If any of these wires break, or multiples of them even, if this wire goes down between here and there, I have 1, 2, 3, 4 other ways of getting to this computer, of having it route that way. We will see networks, local area networks, designed this way on occasion, sometimes especially in a server room environment, where you do want to have a lot of high redundancy, high-speed connections between servers. Not typical in a general production area of a network. This is much more of a concept of what the internet is like. And that's what makes the internet so redundant and so versatile, is that we have multiple connections between host sites. So instead of having computers, these would be locations of having, if one link goes down, that's okay, we can still get around it. Obviously, the disadvantage is that for every device you have to have a separate network interface card. So if I want to add just one more computer here, each of these computers would have to have a separate network interface. Question? Okay. Feel free to ask questions. Okay. Going back to the star is the most popular because it's very easy to use. Yes, you have the central connectivity device, but it's really easy to add another computer. If I want to put another computer out here somewhere, all I do is string a line from that central device out to that computer, put another one out over here. It's extremely easy to expand. Probably the biggest advantage is dealing with troubleshooting. If this connection is broken for any reason, the entire network does not go down. In fact, nothing is affected on the network except this single computer. So again, it's very easy to troubleshoot. If this computer is not connected, it's this connection somewhere that we're looking at. So I can avoid even looking at these computers. On the other hand, if all the computers are affected, if everything cannot print or connect to the internet or whatever, I might be looking at the central device, the central switch, as the possible point of failure. Most likely would not be something on this network card or this operating system and this one and this one. We're looking for commonalities. So it's very, very simple to troubleshoot and very efficient and easy to expand. It's also nice for traffic. All the traffic is controlled, especially with the switch. If this computer is talking to this computer, it just goes from there to there. On all these other networks, if this computer wants to talk to this one, it has to go all the way around the loop. And then to finish that conversation, it has to finish back around the loop. And so, and in the meantime, none of these can talk. Only one person can talk at a time. So those are the advantages and disadvantages, sort of the overview of them. A network technology, practical application of a topology and other critical standards, provide method to get data from one place to another. It defines many aspects of the network, from the frame types to the actual cables to the little plugs and connectors that are used, anything that's needed to get data from one computer to another. Data is moved from one computer to another in frames. A frame, there's some pictures later on. I'll back up. In order to start with frames, we need to address, it's like a package. I need to tell it where this frame is going to go. And we do that with a built-in identifier called a MAC address, which is the Media Access Control address. It is 48 bits long, giving 281 trillion MAC addresses. That's a lot of MAC addresses. We're not running out of those, not anytime soon right now, but that's what we have right now, is the 48 bits. MAC addresses are binary. That is, in fact, 48 ones and zeros. That's really long and difficult to write that out, so we do shorthand. And if you are taking or will take math and logic, you're going to learn that hexadecimal is just shorthand for binary. For every 4 bits in binary digits, I represent that with 1 hexadecimal digit. So 48 bits is going to equal 12 hexadecimal characters. Anything that connects to a network will have one. Your computer will have one. In fact, on a laptop, if you have a physical NIC, a wired NIC, and you have a wireless NIC, that's going to be 2 of them. Bluetooth can also be used for networks, so that may have one as well. Your cell phone, how it connects to the internet, is going to have a network interface. A MAC address, because it has a network interface. The MAC address is a way of uniquely identifying any object on any network. That's how I talk to you. It's just like a street address. 123 Main Street is how I get a hold of you on that street, of how I want to talk to you. Or it's even think as a phone number. If I want to call you, everybody has a unique phone number. 2 people with the same phone numbers just doesn't work. So we've got to keep those unique. Here's a picture of it in Windows, system information. It tells, if you do run in system information, it can tell you all kinds of stuff. I'll go ahead and just show mine real quick here. If I want to run system information, and it brings this up, all kinds of information underneath here. In fact, we covered this last week in class. But under components, I have networks, and then under networks, I can take a look at the protocol. No, my mistake. Under adapter, so network adapter is what I want to look at. Now I have a lot of different adapters. Here's an adapter. There's no addressing on it. And sort of scroll down. Let me find my actual network interface card. And it's right here. So I have an Intel Gigabit network connection. Here's the adapter type. We'll talk about Ethernet later on. It's Ethernet 802.3. The product is an Intel 82577LM Gigabit network connection. Coming down here is my IP address. 172.16.193.2. My subnet mask. Those things go together. We'll talk about that later in the class. And a little bit further down is my MAC address, is 68B599EF7348. So again, this represents 48 binary digits to uniquely identify this adapter on a network. Frames, coming back to frames again. A frame contains the MAC address of the network card to which the data is being sent. It has the MAC address of the network card that sends the data, and the data itself, so I'm sending something in it, and then a way of verifying or checking that information. There's lots of different types of frames or frame types, but this is the general things that they'll all contain. How big the data can be, or what kind of error checking is going to be on there, or how many bits of padding, or how big or how small it can be. That's the variations in it, but they all have this. It's just like sending a letter. It's not any different whatsoever in that you have an envelope, and the very big center thing in the envelope is an address. Where is it going to? Well, that's important, but we also want to know where it came from so that we can reply to it. If I didn't have that little label in the upper left-hand corner to say where it came from, I'm not going to know where it came from if I need to reply, or if something happens in the mail process. How do I return to sender because a link failure somewhere if I didn't know where it came from? So obviously why we're connecting is to send data. In networking, you learn more about that data will not fit in these, and so it's actually chunked and it's segmented to make it fit. So you have a large picture and it's all chopped up into little tiny pieces, and then each one of those pieces is then addressed and sent separately, just like putting an envelope, a letter inside of an envelope, and then you address the outside of each one. Unfortunately, we don't have this in real letters, a way to verify the data we received in good order. It's called a CRC. Kind of the best example might be like letter confirmation or signing for it, but that doesn't actually verify the contents of it. So electronically, we can do some extra stuff. The frames have to match the cabling, the connectors, and the devices on the network. So when we have a specific type of network interface card, it supports certain types of frames or a specific frame type. Same thing with the physical cable. Running fiber, we can support a different frame, or we use different frames than we do with the Category 5 cabling. And then, of course, the switches or the central devices that we're working with. This is a generic frame, and here's a picture of it. The frame is the entire object. So this whole thing is the frame, and it is just a series of ones and zeros. And this is why you have to define the frame, and so that as I'm reading it, that I know how many of those bits are for the MAC, or the recipient's MAC address. And then what's the next section of the senders, and then how many bits do I keep reading that are going to be the data, and then how to do the error checking. So again, the frame will define all that. Otherwise, it's going to look like a whole bunch of ones and zeros. And the frames are one after the other. So it's going to keep going 1 0 1 0 1 1 1 0 on and on and on. What do I read for where? Where did Ethernet come from? It was sort of a group effort by Digital Equipment, Intel, and Xerox. They developed the actual first connections of getting computers to talk to each other, and that eventually became the Ethernet standard. Ethernet was primarily developed by one man, Bob Metcalf, and he was working at Xerox, Xerox PARC, which is their research center. And it's pretty interesting watching some history on that of how it was developed and the thought process behind it. That's in the mid-70s, and we're still using it nearly 30, 40 years later. Ethernet's gone faster by a couple different ways. The same concept applies of how Ethernet, uses frames and sends things in and out to the network. But how it gets to be faster is starting with the cabling. These are electrical connections between these computers. If I can make those electrical connections carrying it faster, more quickly, less interference, I can go through faster. The network interface cards need to catch up with that or keep up with that, and so they need to be updated as well. So there's definitely, the whole electronic side or the physical side of Ethernet is getting faster and faster. Then there's other ways of making it faster as well, sort of tweaking the frame types and, what's going on inside the actual frame itself. Modern Ethernet networks all use a star bus topology. Now, what that means, this looks like a star. So it's a physical star topology. You have a central device and everything's branching off of it. So that's definitely a physical star. It's looking that way. Logically, this computer wants to talk to this computer, so it sends the frame through the wire, and then inside the switch it says, oh, you want to talk to that computer based on the MAC address? I will make a connection. If you ever watched the old-time movies about the phone operators, when you literally connected one person to the other with a little jumper cable from one phone to the other, that's what's happening here. It's making a connection from that port to that port. It doesn't affect this computer or this computer or this computer at all, so it's making this connection. What do we call that network? That is a straight line between two computers. Call that a bus. And that's where we get the idea of this is a star bus topology. It's a physical star, but logically, we just have a single line between two computers. If this computer wants to talk to that one, it goes to the switch, makes that connection within the switch, and now I have a single line connecting these two, which makes it a bus. So that's a star bus topology. This is a picture of a little switch. It's nice, for a home use or a very, very small office. It looks like it might have 8 ports. Smaller switches will also, you can even find a 4-port switch or a 5-port switch. For companies, though, they'll make typically 24 or 48-port switches. So one big box that has 48 different connections on there that you can connect everything together. How we connect them together is using unshielded twisted pair cabling, or UTP cabling. We also talk about shielded twisted pair. It's exactly the same, except it has an actual shielding around the cable, so an extra wrapping of very thin metal to help keep interference down. UTP, specified cabling for 10, 100, 1000 base T. And they don't get much into here in this chapter about what these are. You definitely will in networking 1. But this is the speed of the network. So this is 10 megabits per second, 100 megabits per second, or 1,000 megabits per second, otherwise known as gigabit. Base means baseband. Baseband is a digital connection, so these are all digital connections. And T specifically means twisted pair. If I was going to run this across fiber, I could still do 1,000 base, but then 1,000 base F for a fiber connection instead of a twisted pair. There are different types of twisted pair cabling. They range anywhere from 22 to 26 gauge wires, and they're twisted together in pairs. So we have a green pair, so it's green and white, and then we have a blue pair, blue and blue white, and so on. The pairs stay together, and we end up having 4 pairs. So there's 4 different connections that are going on. Each pair of wires makes one circuit between the initiating computer and the receiving computer. So there's 4 channels or 4 loops or 4 circuits that are actually being created between both the computers. We do have different CAT levels, we call them categories, or CAT 1, CAT 3, 5, 5E, 6, and 6A. The newest standards are 6 and 6A. 5 and 5E, especially 5E, is extremely popular. You see lots and lots of that installed over the last many, many years. Here it talks about sort of the different levels of categories. Category 1 is your standard telephone line. You really can't put data across there. It's really just meant for some voice. Category 3, popular for a while, 10 megabits networks. A variant of that could be used for 100 megabits, but really we're looking at minimum of category 5 for 100 megabits networks. 5E, which is a slight enhancement to the 5, allowed the pushing of gigabit or 1,000 megabits per second. Once we get into category 6, we're truly looking at the gigabit networks. And at shorter distances, we're looking at 10 gigabits. 100 meters, by the way, is pretty much the length limit of any Ethernet that we're looking at ever, even going back to category 5. This 100 megabits network was only supported up to 100 meters. And that's going to be really, really important to remember that as you're laying out networks, that you really have that 100-meter limit in laying out physical wires. That's roughly 300, 330 feet that you're limited to. Category 6A takes that 100-meter limit, but allows you to do 10 gigabits across that. I've never worked with things like that before. School, as they put new wiring in, like this classroom, it's all using category 6 cabling. Little difference between unshielded and shielded again. The unshielded twisted pair comes in 2 formats, or two categories, or 2 specifications. It's the TIA EIA 568A and the 568B standards. And there's a chart coming up sort of showing what those are. Shielded twisted pair, same thing we just talked about. It's just surrounded by an extra protection of shielding to protect from the electromagnetic interference, which we talked about in the last couple of chapters, dealing with trying to eliminate that kind of interference with our computer. Cables will also be labeled. Sometimes it's really hard to see, and sometimes it can be worn or something, but they'll always be labeled somehow or another of what category they are, so whether they're category 5 or 5E or 6. Implementing the Ethernet, 10, 100, 1000 base T. The 10 and 100 really only required 2 pairs of wires. So that means 2 circuits that it's doing. It's going to use 1 pair for sending and 1 pair for receiving. As we moved up the different categories and looking for that extra, 1,000 base T or 10,000, we're using all 4 pairs of the wires, 2 for sending and 2 receiving typically. For the connectors in the end, we really have 2 types of RJ connectors. It's the RJ11 and RJ45. We're only using the RJ45. That's the only thing we use for unshielded twisted pair connectors. RJ11 is only for the telephone lines. Looking at the RJ11, it's a thinner. It only supports so many wires, where the RJ45 has 8 wires in there. Exactly the same form. Essentially, it has a little clip on here. You can sort of see the little clip on there where it snaps into place so it can't just be pulled out. Here's another view of it, of what the connector is. Knowing the pin numbers will be important in your networking class, not so much in this class, but knowing that this is going to be pin 1 on the left-hand side, reading left to right, when the clip is facing away from you, and the wire actually runs out this side. So you're holding the wire towards you, having the pins away from you, and the clip that goes into the receiving socket on the bottom. This is pin 1, this is pin 8, and we'll see why in just a second. We talk about the A and B standards and the colors, and these are the colors. This is not a color-coded chart, unfortunately. There's some really, really good color-coded charts out there. So if you take a look at them, you can see what the standard is. In Networking 1, you'll be memorizing these and making the cables and making sure that if you're using TIA 568A, that you can put the white-green wire in pin 1, the green wire in pin 2, the white-orange in 3, and so forth. If you're making the B standard or the B specification, then you're just switching these wires around a little bit. Protocols, LANs, and WANs. Network protocols. Network protocols take the incoming data received from the network card, keep it organized, and send to the application that's needed. You'll be talking a lot about the OSI model and different protocols of how things work. Protocols are just a set of rules. There's a protocol for almost everything that we do. There's a protocol for eating at the dinner table. Is it acceptable to throw food and to put your feet on the table or whatever? That's not part of the protocol. Part of the protocol is to be polite and ask for things, whether there's protocols for driving your car, there's protocols for talking on the telephone. And the whole reason is to keep things organized and actually make things happen. If there's no protocols, no rules, anybody does whatever they want. I couldn't talk to you and you couldn't talk to me. So protocols make that happen. They take care of really essential things such as addressing and security. So if we talk about the protocol suite or a group or a protocol stack of like the IP stack, which is the IP protocol, it's going to involve things like how do I name this? I give it an IP address. How do I deal with security? Well, I work with it at this level, and all kinds of other functions. Going back a little bit, we will start with some of the earlier protocols. It was NetBIOS and NetBEUI. In the 1980s, IBM developed the NetBIOS Extended User Interface, the default protocol for early versions of Windows. The underlying protocol stack for this was NetBIOS, NetBEUI. NetBIOS did the naming part, while NetBEUI did the framing part and actually made it connect. NetBIOS names are very simple. They were just nothing is allowed except upper letters, numbers, and a few special characters. It's great for small networks, but relied on individual computers to send out frames, address the MAC address, FFFFF, all Fs, which is a broadcast address, which means it goes to everybody on the network. So I didn't address something to you, say, hi, I'm Paul, I'm sending something to Bob. I'm just saying, hey, I'm saying this to everybody, and if you happen to be Bob, then you listen and everybody else just sort of get it too, but kind of ignore it. The larger the network, the more bandwidth broadcasts eat up. So going back to the example of looking at those other computers, not only am I just communicating with that one computer in the network, but I'm communicating with everybody on the network. And while I'm communicating with them, then they can't communicate with anybody else. So it really ate things up. By the mid-1980s, it was clear NetBIOS wasn't going to work for large networks, so a new protocol was developed. Here's an example of a broadcast. Could the computer called Mike's PC please send me a frame back to tell me your MAC address? And sort of communicate that way. Local area network. LANs, routing, and WANs, a local area network. A group of computers are close to each other. Almost always a group of computers are able to hear each other when one of them sends a broadcast. Not a great definition. It really sounds like the literal thing, like I have to hear you, I have to be in the same room. That's definitely not the case. LANs can span multiple floors and even the same building, even potentially multiple buildings. A LAN is kind of what it's saying is when one computer sends a broadcast, everybody else will hear it. To break that up, if there's too much communication going on, we break that up into broadcast domains, and we use things like routers to do that. A switch will extend a broadcast domain. Take a picture at one. Here are two broadcast domains. They're two different broadcast domains because they're two separate LANs. If this computer sends out a broadcast message, you'll go to the switch, and the switch says, I'm going to talk to everybody on this network. Now, this is not going back to NetBEUI, NetBIOS stuff where we're always communicating this way, but that's how we define a broadcast domain is if I were to send a broadcast, who would hear it? So if I send a broadcast from here, only these computers would hear it. Likewise here, if this sent a broadcast, it's going to hit the switch, and it's going to go to those devices. If I connect these two switches together, I'm extending that broadcast domain. And if I were then going to send a broadcast from here, it'd go out to the switch, out to this switch, and everywhere else as well. So a switch just extends the broadcast domain. If we want to break it up, we would essentially become a wide area network. A wide area network is a widespread group of computers connected using long distance technologies, usually connecting via one or more routers. Again, I'd really struggle with this definition. It's a wide group of computers connected using long distance technologies. Kind of like in this picture here, they're right next to each other. If I put a router in here, like this picture, here's a router. That is two different broadcast domains. This whole thing is a wide area network. This is not a long distance technology. They're physically next to each other. If you really keep it clear that a LAN, I guess very simply with our networks, is if it's connected with a switch, it's a local area network. So this would be a local area network over here, and this is a local area network over here on the right-hand side. Once I connect them together, this whole thing becomes a wide area network. Don't think of them as close together or far apart. That can be misleading. You can have WANs that are next to each other, and you can have LANs, you know, across buildings. TCP/IP, so the next protocol beyond the NetBEUI, NetBIOS. The suite of network protocols invented in 1983 quickly became the de facto protocol suite for any computer connecting to the internet. This still wasn't necessarily the default or the de facto standard with working with local area networks. That didn't come until later on when the internet became more popular with businesses. But it certainly was anything that connected to the internet at the time would be using TCP/IP. It's an IP protocol. Like we said, protocols deal with such things as addressing. IP address is the unique identification number for your system on the network. Just like we have a physical address, a MAC address, which identifies that computer anywhere in the world, it's not structured though, it's not hierarchical, or I would have a very, very difficult time finding you anywhere in the network. So IP addresses sort of break that apart and make it sortable or searchable. We have two different parts in your address. It defines which network you're on and then which computer you are on that network. The biggest thing that we really concentrate on this level is the network side. How do I get to that network? There could be 500 computers in that network. I don't care which one you are at this point. I just want to get to the right network. And start at the mail delivery process. If I have a mail, I use a two-part option as well. I use 123 Main Street. Main Street's the street that you're on. I want to get all the mail to Main Street. Then I sort it out to what house it is. But first I do it to my Main Street. So I have different piles, one for Main Street, one for Washington Street, one for Park Avenue. I clump everything together, and then I take it there and then deliver it to the individuals. If I was doing physical addresses like Bob, Larry, Sue, and Sally, that's great if I'm just working in a neighborhood. If I'm delivering mail across a city that way with just using people's names, I'll be running all over the place and trying to find these people, and it wouldn't be very, very efficient at all. Just like MAC addresses have a very discrete way of describing them, IP addresses do as well. They contain 32 bits or 32 binary digits. We don't represent them the same way as we do with MAC addresses. MAC addresses, we have 48 binary digits. For every 4, we're going to substitute that with a hexadecimal. In IP addressing, what we do is we cut up that 32 bits, or those 32 binary digits, into 4 8-bit segments. What's nice about a bit is that the 8 bits is that 8 bits is a single byte. So really what we're saying is an IP address is 4 bytes long. How do I represent each byte? I take each byte, convert it to its decimal equivalent, and then, which our value is from 0 to 255, put a dot between each of those, and that becomes our dotted decimal notation. So again, I take my 32 bits, split it up into 4 sets of 8, we call those octets, and then put the digital equivalent the decimal equivalent of each of those. It's really nice for writing things and keeping, sort of in your mind. It's kind of easy to remember, 172.16.32.9, pretty easy to do. It's not very representative of what's really going on in there. When you get deeper into working with IP addresses, you end up converting all of those digits back to binary again, out to their full, complete 32 discrete ones and zeros. Every computer in the same broadcast domain will have a common network ID. It's a network address. How do I know which of those 32 bits are part of the network ID? And that's the subnet mask. The subnet mask will say you use the first 8 bits for the network ID, or use the first 12 bits or the first 20 bits. It tells you that. IP addresses and their subnet mask always have to go hand in hand, otherwise you don't know how to divide that 32 bits up. The default gateway is the way for your computer to get off your network if you don't know where you are going. Here's a picture of it. Here's a nice little happy network. This computer can talk to that computer can talk to that computer, and all around. If I have a server sitting over here, they can talk as well. Suddenly, somebody wants to get out to the internet or get to another computer someplace else. I can't directly talk to it. It's not capable of doing that. How I communicate then is I take my frame that I'm sending out here and I send to my switch, and it will then go out to the router, because my default gateway, when I define it on this computer, it tells me you want to connect to something that's not on my network, send it to me. Can't think of a really good real-world example of that. It's almost like a help center in a mall, an information center. I don't know where this is, so this is my place to go. Everybody knows to go there. This computer too. If I want to get to CNN and you're not on my network, I can connect to it, so I just give it to you and let you take care of that. The message actually gets sent out from this router, eventually gets to CNN, comes on back, and then the reply makes it back to that computer. If I want to go to eBay on this computer, it's not on this network, so I'm going to send that message to the router. You're actually sending the message to the router. The router figures out which network it needs to get to and eventually gets it out there. Okay. Domain name services. Actually, we're going to take a quick break here. We'll come back and work with domain name services and sort of finish up the chapter then.